Hello everyone. So we'll discuss about transitive closure. Let's assume that we have this relation with the ordered pairs 1, comma 2, 2, comma 3 and 3, comma 4. Now, the same thing can be denoted as a diagraph in this way. There is an edge between 1 to 2, then an edge between 2 to 3 and there is an edge between 3 to 4. Now, if we decide to add transitive edges, we had briefly discussed the concept of transitive closure before. Basically, what is the smallest relation that we need to add or take the union with the given relation. So this given relation has only three ordered pairs 1, comma 2, 2, comma 3, 3, comma 4. What more pairs do we need to add to this relation so that the entire relation, the result becomes transitive? So we'll go through this example and we'll find a transitive closure. So first thing that we can observe is there is an edge between 1 to 2 and there is an edge between 2 to 3. Now, if the relation is to be transitive, there should be an edge between 1 to 3. That is starting from 1 to 3, directed from 1 to 3, right? So we have added this edge. Okay. Now let's take a look at some more transitive relations over here or some more transitive pairs that can be formed. 2, comma 3 and 3, comma 4 exist. Therefore, 2, comma 4 should be added. So 2, comma 4 is added. Anything else? Because there is 1, comma 2 and 2, comma 4, there should be an edge 1, comma 4 or 1 to 4. Okay. So red edges are added during the first iteration and then the teal colored edge that we added was during the second iteration. Okay. The blue indicates the original graph. Then we first found that 1 to 2, 2 to 3, therefore 1 to 3, that was how 1 to 3 was added, and then 2 to 3, 3 to 4, so 2 to 4 were added. And now with these new edges, 1 to 3 is a new edge, like 1 to 3 is a new edge, right? This 1 to 3 is a new edge, and 3 to 4. Or if you consider 1 to 2, which was the original edge, and 2 to 4 is a new edge. So the red ones are the result of the first iteration. And when we consider the original edges which were in blue and the edges added in the first iteration which were in red, we get this new edge 1, comma 4 which was added during the second iteration. But see, if we do it like this, it will be quite time consuming and it is possible that there may be human error and we may, miss some edge in case of larger graphs, especially. Okay. So I had discussed this concept before. So before moving on to the next part, I will quickly revise the concept of what exactly R means, what exactly R square means, R cube means. Okay. When we take composition of the relation with itself, what are we doing exactly? So if you remember, we had discussed this concept in the class 6 degrees of separation. The idea that everybody in the world is connected by 6 degrees of separation. So you know someone or have met someone, that person has met someone else, and so on. And likewise, if you take any two people in the world, so there will be at the most 6 degrees of separation between you and that other person. So that is kind of a hypothesis or conjecture, you can say. So now 1 degree of separation means you know or you have met somebody else. Okay, if you remember the example that I have given, you can comment down below in the video. So let R be a relation on the set of all the people in the world, and A comma B belongs to the relation R if the person A has met person B. So 6 degrees of separation for any two people A and G means A has met B, B has met C, C has met D, D has met E, E has met F, and F has met G. And therefore they all are in R. Okay. So therefore you can say that A comma G belongs to R raised to 6 because there are 6 degrees of separation. Okay, so the power that we raise R to, that is the power of R indicates the degrees of separation. So that leads us to the concept of connectivity relation. What does R mean? R contains edges between all the nodes reachable via one edge. R composition R, that is R square, contains edges between nodes that are reachable via two edges in R, that is 2 degrees of separation. R square composition R is equal to R cube, which contains edges between nodes that are reachable via three edges in R. In general, therefore, R raised to n means it contains edges between the nodes that are reachable via n edges in R. Now, star, this is also indicated as R raised to infinity. R star or R infinity. Connectivity relation is indicated in some literature as R star, and in most literatures it is also indicated by R raised to infinity. Okay, R star or R infinity, both are the notations used for connectivity relation. Okay, so R star or R infinity contains the edges between the nodes that are reachable via any number of edges via any path in R. That is, basically they are connected. Okay, if R infinity or R star contains 1 in a particular position, that means those two vertices are connected. Maybe by one edge, by two edges, by four edges, whatever, but they are connected. Okay. So you can rephrase this as R star or R infinity contains all the edges between the nodes A and B where where n is a path. Okay, when is a path of length at least 1 between A and B in R. Okay, so there is a when there is a path of length at least 1 between A and B in R. Okay, so now the theorem or the theorem basically is what we are saying over here is R star or R infinity is nothing but the transitive closure of R. Okay, one way to obtain Rn or basically R star, one way is you can say that it is R union R square, okay, union R cube, and so on up to union R raised to n. And as I had told you during the lecture, where do you stop? For example, if R raised to 3 and R raised to 4 are the same, then you don't calculate the further powers. You just stop there. Or if R square and R cube are the same, then you will just stop at R square. Okay. So that is one way of finding R raised to infinity. Another way is by calculating the transitive closure of R. Okay. So in short, what we are saying over here is R infinity and transitive closure are one and the same. They are exactly the same. So definition of a transitive closure is that there are edges between any nodes A and B that contain a path between them. Okay. So if there is a path between A and B, like ultimately that is what had happened in our example before, right? Here, if you see, initially there were no paths between 1 and 4. Well, like there was no direct edge between 1 and 4. But see, if you consider, is there a path between 1 and 4? Yes. So 1 and 4 should be connected. Is there a path between 1 and 2? It's a direct edge. Is there a path between 2 and 4? Yes. So 2 and 4 should be connected. Is there a path between 1 and 3? Yes. So 1 and 3 should be connected. And that is what we in fact got after taking the transitive closure, right? So that's the idea of transitive closure, and that is equivalent to the connectivity relation. Okay, so R star or R infinity, okay, is the star closure, okay, also called as R infinity. I'm emphasizing this point. R infinity and R star are both the notation for the same thing. So R star or R infinity or connectivity relation is the star closure of relation R, and it is defined as the transitive closure of a relation. So the transitive closure of a relation R is the smallest transitive relation containing R. So TR is the transitive closure, and it is same as R raised to infinity. Okay, now how do you find a transitive closure if you are not doing it by like actually drawing the edges on the graph? You have to do it using matrices. So what you will do, so let MR be the 0, 1 matrix of the relation R on a set with n elements. So that means it's an n by n matrix because The base set contains n elements, and it is a 0 1 matrix. The entry MRIJ will be 0 if there is no edge between IJ, or its I is not related to J, and there will be a 1 if I is related to J. Okay, IJ will be 1 if I is related to J. So then the 0 1 matrix of the transitive closure is obtained by this procedure. MR, now in case of relations, we take the union, right? We take R union um, R square union R cube and union R raised to n, right? That gives us R star or R infinity. But in case of matrices, this operation is called as join. Now let's see how it is done. So MR, again repeating the point for emphasis, nodes reachable with one application of the relation will be indicated, or which can be found out using MR. MR square will indicate nodes reachable with two applications of the relation, and generalizing, nodes reachable with n applications of the relation will be uh, indicated in MR raised to n. Okay. So now let's say this is the matrix, and we'll go all the way and we'll find its transitive closure. Now, just for the sake of understanding, how does the diagraph of this relation look like? So there is a self loop on, okay, if we label these as, let's say, 1, 2, and 3, okay, so there is a self loop on 1, there is a self loop on 2, there is an edge between 1 to 3, there is an edge between 3 to 1, and there is an edge between 3 to 2, right? So this is how the diagraph of this relation looks like, right? And if we continue, now this is what is the final thing to be calculated. Now here what we are doing is, firstly we are calculating MR square. Now notice how it is calculated. So we are doing matrix multiplication. Okay, 101 multiplied by 101. Okay, now how would you do matrix multiplication of these two rows normally? You would say that in order to obtain this element, we'll do it for any two elements within the matrix for your understanding. So let's say how this particular element is calculated. You take the row 0 of the first matrix, you take the column 0 of the first matrix, and then you take the dot product. So basically, you would do matrix multiplication like this: 1 into 1 plus 0 into 0 plus 1 into 1, something like this. Now, because this is a Boolean matrix, this is called as a 0 1 matrix, or this is a Boolean matrix. I had used this terminology in the lecture as well. This is a Boolean matrix, right? So we use Boolean operations. So this will be 1 and 1, right? And this will be or 0 and 0, or 1 and 1. So this is the ultimate result will be 1, right? This is 1 or 0 or 1. Ultimately, it will be 1. Now let's examine an entry which gets a 0, right? So this is um, row 1, column 2. So we'll take row 1, we'll take row 1, and we will take column 2, right, to obtain this. Okay, so if we find the product of this, I will draw it over here below. So this is 0 into 1 plus 1 into 0 plus 0 into 0. And in terms of Boolean logic, if you say, it is like 0 and 1, or 1 and 0, or 0 and 0. So ultimately it comes out to false or 0, okay, which is the entry that we get over here. So likewise, we find the composition or the product of the Boolean matrices, which is in this way, and you can also call it as Boolean product or whatever, but it's simply matrix multiplication, and only the thing is multiplication and addition are replaced by and or. Understood? So now let's move on to the next part. So this is how the MR square ka diagram looks like. Okay. If you see the matrix, what is added additionally now, this particular thing is new in this. Okay. So there is a self loop on 3 that is added. Now make a note of this. So we have MR square and we have MR. So now next we'll calculate MR cube, which is MR square into MR. Again, the same exact matrix multiplication. You know matrix multiplication, how it's done, so I'm not going into the depth of it. and this is the final diagram that you get. There is no change in fact. As you can see, mr cube and mr square are exactly the same, and that indicates that there is no point in finding mr4. Okay, mr4 will also be the same. Okay, because again, how will you find mr4? It will be mr cube multiplied by mr, right? And because mr square and mr cube are the same, so therefore mr4 will also be the same. So no point in going ahead in higher powers. So now you find the join. Okay, now join, or simply you can think of this as OR only. Okay, so this one, just see the elements in the corresponding position. This is the position 0 comma 0. So that here there is one, here there is one, here there is one. 1 or 1 is 1. Now here there is 0, here there is 1, here there is 1. So 1 or sorry, 0 or 1 or 1 is 1. Again 1 or 1 or 1 is 1. Then 0 or 0 or 0 is 0. Then 1 or 1 or 1 is 1. 0 or 0 or 0 is 0. So likewise you do element wise OR. Okay, it is called as the join of matrices or whatever, but element wise OR you are doing basically, and that is how you find MR infinity. This is MR infinity that you are finding over here. This is the join or union of MR, MR square, and MR cube. Okay, actually, this was not even necessary MR cube, but we have calculated MR cube, so doesn't hurt. We find the union, but as you can see, they're exactly the same. So we could have stopped at MR square as well. After we found that MR cube is the same, like OR में तो it will not matter if, even if you just take the OR of MR and MR square. Anyway, so this is MR infinity. I hope this procedure is clear. Now, what is the time complexity of this procedure if you see? Okay, what we did, we computed the next matrix every time, that is mr to the power I, right? And then we did a Boolean join with the previously computed matrix. So for example, let's say instead of finding all the powers first and then finding the join, let's say we did this. We first calculated mr square, that is mr composition mr or mr Boolean product mr, and then we joined that with mr again. So first we joined it. Instead of going for MR cube, first we joined it there itself. Okay. So MR join MR square. And then we again computed MR cube, which is MR square Boolean product MR. Okay. And then we took the join, and we could have stopped there when we found that, as I told you, okay, MR cube is exactly the same as MR square. So there is no point also in taking the join with MR cube because it's the same as MR square. Okay. So, transitive closure algorithm improves this, right? So, procedure transit now, sorry, transitive closure. This is the transition algorithm, and this is what we did. Just expressed as an algorithm. So, we started with MR, and then we saved the A in B. And what we do is we just take the Boolean product with MR again, and we take the join with A. Okay, and finally B will contain the 0, 1 matrix of R infinity, right? The same procedure as has been shown over here, right? We are doing the same thing, right? Now, what is the time complexity? You can pause and just think about it. What is the time complexity? There is one loop, right? How many elements does it have to do? Now, this matrix product, all of you have done in C, right? So, what is the time complexity? How many nested loops are there in matrix multiplication? And therefore, what is the time complexity of this step? Because this is simply matrix product, matrix multiplication. And additionally, there is a nested loop outside of them. So, this is order of n time complexity. And iska complexity kitna hota hai? You can pause if you want and think and recall. The time complexity of this step will be n cube because matrix product involves nested loops, three nested loops. So this will be n cube, and that is inside a loop which also runs n time. So it will be n to the power 4, right? So order of n to the power 4. Now, can we improve it? Can we go from n to the power 4 to n to the power 3, which will be a huge, huge kind of an optimization? Okay. So this is the principle. Okay. This is the fundamental principle behind this algorithm that we'll study. Basic principle, can say fundamental or basic principle. What's the basic principle? Consider the kth row, consider the kth row and kth column. So you will see there are many horizontal and vertical strips moving around. So there is a horizontal strip which indicates the kth row, and there is a vertical strip which indicates the kth column. And if you find that for the jth element within the kth row and for ith element within the kth column, i- if those are both 1, then their intersection should be changed from 0 to 1. Okay, so you will only focus on the kth row and kth column, and there you will see that is there any such combination कि यहाँ पे 1 है यहाँ पे भी 1 है, तो then their intersection should also become 1. Okay, so in that way we move from rk minus 1 to rk, that is, let's say from r to r square we'll move, uh, then from r square to r cube, and that will be clear with the example. Okay, so let's say this is the example relation that we have. A comma b is 1, b comma d is 1, d comma a is 1, and d comma c is 1. Okay, so this is the original relation, r raised to 0 or just r. Okay, now what do you observe over here? Okay, now this is right now, this means this k equal to 0, right? So I'm going for 0th row, my strip is at 0th row, and my strip is at the 0th column over here, right? Now I find the intersection. So 0 1 0 0 0 0. So you just take the combination 0 0 0 0 0 nothing. Okay, 0 hai and 1, 0 0 0 0, no change. Now here you will find a change. There is a 1 over here and there is a 1 over here, right? So therefore their intersection over here should be changed from 0 to 1. Got it? So therefore that was changed from 0 to 1. Okay, so this is changed from 0 to 1, and we'll directly move to next step. Directly moving to next step. Now, because this was k equal to 0, our horizontal strip is on 0th row, vertical strip is on 0th column. Now, when we are finding R1, okay, k equal to 1, then our vertical strip is at k equal to 1 column and k equal to 1 row. Okay, so now again you have to find intersection. So I'll always start with rows. Okay, so this is 0, 0 intersection with 1, no problem. 0 intersection with 0, 0 intersection with 1, you can ignore that. Okay, now let's ignore all the zeros. Okay, now just focus on this 1 in the row. Now, what can form a good combination with this 1 in the row? There is this 1 in the column and there is this 1 in the column. So what is their intersection? This one and this one. This is their intersection, right? So now this will become 1. Okay, because this is at the intersection. Similarly, there is a 1 in the row over here, there is 1 in the column over here. So their intersection is this. Okay, just focus on the ones, their intersection is at this position. So this should become 1. Okay, so our R1 will get ones added over here. Okay, and this is our R2. Now in R2, we will consider k equal to 2 column and k equal to 2 row. Okay, column number 2 and row number 2. This was row number 0, row number 1, row number 2. Ignore all the zeros. There is only one 1 and there is no other one anywhere else to form a combination with this one. So therefore there will be no change between R2 and the next one. Now in case of R3 there are many ones. So something interesting is gonna happen. So there is a 1 over here. Now let's see the combination of these ones with all the ones in the column. So this one and this one combines, this one and this one combines to change this element from 0 to 1. right? And then this one and this one will combine, right, to change this particular element to 1 again, right? So this will also be 1. Okay, so that is for this one. Now let's move on to the next one. So this one will combine with this one, but this is already 1, so no change. This one will combine with this one, and now this element will also be 1. Okay, and this one cannot combine with anything else. That is fine. Okay, next. Now this one will combine with this one. Okay, and okay, their intersection is this, so this will become 1. So this one and this one will combine, their intersection will be 1 again, right? So yeah, we are done. So our final r raised to 4 will look like this. Did I miss anything? No, right? So this is r raised to 4, and this is our final transitive closure. Nothing else is left. This is our final transitive closure. And now this is the algorithm. This algorithm is called as the Warshaw's algorithm, and it uses only the order of n cube operations. So what do? We initialize R0 with A, then we go from k equal to 1 to k equal to n, I equal to 1 to n do. So this is a triple nested loop. The main operation is you examine the element. Okay, you examine the element at position ij. Either it is 1 beforehand, or when will the you know uh, when will rkij become 1? When either it is already 1, or rk minus 1 ik and rk minus 1 kj, both of them are ones, then the result will also be 1. I don't need to worry about this algorithm, but this is what the procedure we have done, right? So if in R0 we found that um, I0 and 0j are both 1, then ij will also become 1 in R1 in the next matrix. Okay. And finally, you return r raised to n. Now, wij equal to 1 means there is a path from I to j going through the nodes less than equal to k. Indices I and j may have index higher than k, right? So basically, it means that are there any paths between I and j? When k equal to 0, it means are there any paths between I and j going through these nodes? So okay, so for example, here it meant that is there any path between b and d which is going via a? Okay, so that is what we are trying to find. Okay, so this means there is a path from A to B, and there is a path from D to A. That means, okay, so what does this mean? There is a path from A to B, and there is a path from D to A. That means this should be 1. That means there should be a path from D to B as well, going via A. Similarly, we find all paths going via B, all paths going via C, and all paths going via D. Okay, and that is how we find a transitive closure, or in other words, we also find R infinity. Okay, so Walshall's algorithm is used for finding transitive closure. It is used for finding R star, you can say, or it can be used to find R raised to infinity. Okay, connectivity relation, transitive closure can be found using this procedure if you have to do it using Warshall's algorithm. If you are asked to do it using matrix multiplication, then that is another way. That is n raised to 4 complexity. Okay. So that's it for this video. If you have any questions, any doubts, do post them in the comments below. Thanks for watching.